In this section, we will talk about solving word problems or applications in which the equation we set up to solve the problem is a rational equation. So that's why these are coming up in Chapter 7, where we're talking about rational expressions and equations. The first type of problem we're going to look at are called just using proportions to solve problems. So take a look at example 1, read it through a couple of times. So what you want to think about first always is what the variable should represent. And so you look for the question. The question says, how many people in the city might we expect to have a flu shot? So X in this case represents the number of people expected to have a flu shot. So you definitely need, you could maybe shorten that a little bit, but you need to have the, number of people and something involving a flu shot. So you need to be very descriptive about your what your variable is going to represent. So then you want to set up a proportion, and oftentimes there's more than one way to do this, but we could set up 26 of those who were polled had flu shots. So we would say 26 out of the total number polled, which was 250. We would expect that to be the same as the ratio of the people who had a flu shot out of the whole city, which was 50,000. So the people who had a flu shot out of the total number in the poll should be the same roughly as the people who had a flu shot out of the total number in the city. And then, because we just have one fraction on each side, when we multiply by the LCD, it's going to feel like cross multiplication, but officially what we're doing is multiplying this side by 250 and 50,000, and also multiplying the other side by 250 and 50,000. Right, so on the right side, the 50,000s cancel, and on the left side, the 250s cancel. So we've got 26 times 5,000. I'll grab a calculator for that. Where's my calculator? There we go. Sorry about this here. Okay. So we need 26 times 50,000. So that looks like 1,300,000. And on the other side we have 250x. So then we would divide by 250. So we'll get x equals 130,000 divided by 225. So it looks like 5,200. So we could say in our sentence, we expect roughly 5,200 people had a flu shot. And if you want to check, you can see, check the fraction 26 out of 250. See what you get, 0.104, and then try 5,200 out of 50,000. Also the same, so we can check and make sure the ratio really is equal. Looks good. And then another place in geometry where you see proportions arise is in similar triangles. And so the idea is that, let's see, corresponding the ratio of corresponding sides is equal in similar triangles. Let's see if I can spell similar correctly here. So that means like the side we're looking for is x. So if I took x to 12, that should be the same as this other side that we know, 15 to the corresponding side in the smaller triangle, which was 9. We can set it up that way. We can also do, it works to do the same, x to 15. So take these sides from the same triangle and then take the same ratio on the other triangle. Should be the same as 12 to 9. All of that is fine. Right? So either take a side from one triangle to the corresponding side on the other triangle, and a different side from one to the corresponding side on the other. That ratio should be the same, or you can do what we did in the second example here. Let's work through this one. So now officially we're multiplying. The LCD would be, 9 and 12 both going to 36. So 36 on both sides. So then on the right side that's 3x, and on the other side that's 15 times 4 would be 60. So it looks like x would be 20 units. So the missing side length is 20 units. So proportions are one type of problem, and then we'll see just some about unknown numbers, where we usually are talking about reciprocals and quotients and things. So here's an example. The quotient of a number n2 minus a third is the quotient of the number n6. Find the number. So x is the number. That's what our variable should represent. And then we want to translate this sentence into an equation, and as usual we want to just focus on where the equal sign is. So to the left of the equal sign we want the quotient, so we're talking about division of a number and 2, and then we're supposed to take away a third, is or equals the quotient of the number and 6. So there's our equation. And if we multiply the LCD, which would just be 6 on both sides, we'll have 3x. So this 6 gets distributed, remember? So 3x minus 2 from 6 over 3 equals x. If we subtract x from both sides and add 2, we'll have 2x equals 2, so it looks like x is 1. So the number is 1. And if you check, a half minus a third is a sixth, so everything's good. One more about unknown numbers. The sum of the reciprocals of two consecutive integers is negative 9/20. Find the two integers. I don't know if we've done consecutive integer problems in this class. Can't remember. But the setup for those is always, x is the first integer. And if they're consecutive, then they're just one apart. So the next one would be one more than the first one. And it's saying we're supposed to add the reciprocals. So the reciprocal just means 1 over, and it says we're adding them separately, so one reciprocal plus the other reciprocal. So we want to do 1 over x plus 1 over x plus 1. So notice you don't want to do this. That's a different thing. that would be the reciprocal of the sum. And that's not what we want. We want the sum of the reciprocals. So this is what we want, and it's supposed to be negative 9 over 20. Our LCD is a little more complicated on this one. It'll need an x and an x plus 1 and a 20. So 20x and x plus 1 on both sides. And on the left side we have to distribute because there's a sum here. On the right we just reduce. So we'll have negative 9 x squared minus 9x, so when I distribute over there. And on the right, in the first term here, the x's will cancel, so I'll have 20x plus 1, and then the second term, the x plus 1 will cancel, so I'll have 20x. And I can see this is going to be quadratic, so I need to expand everything and get a 0 on one side and try to factor. So 20x plus 20 plus another 20x. So 0 on one side and then factor. And the reason for that is because of this square. So when we have a square, that's our first thing to try always, is get a 0 on one side and try to factor. In chapter 8, we'll talk about what do we do if we can't factor, but we still have a square. But always the first step is to get a 0 on one side. And it's nicest if the coefficient on x squared is positive. So I'm going to add 9x squared to both sides. So I'm going to move it over here to the left. I'm also going to add 9x, so that's going to give me a 49x. And I've got a 0 on one side. And now we have to try to factor this. This is not easy to factor because we have not a prime on the x squared and not a prime on the 20. Let's try a 9x and an x. We know the signs are all positive. So if we work on this, let's see if we have a 9x and an x. The only reason I was hoping that this will work is because I know my answers are supposed to be integers. And if I have a coefficient that's not 1 on both of these factors, neither of them is going to be an integer. So what I'm doing is just the 9x and the x, and I'm hoping that that's going to give me at least one integer solution for one of these factors. And then it looks like if I put a 5 here and a 4, that should work. 45x plus another 4x would give me 49 in the middle. So that's good. So then I'd set each factor to 0. 9x plus 4 equals 0, or x plus 5 equals 0. This gives me x equals negative 4/9. This gives me x equals negative 5. And because we're working on a word problem, this is not an integer, so we don't want to consider that. The question was about consecutive integers, so we only keep this answer. And then the question was, we're looking for two consecutive integers. The first one is x, and the next one was x plus 1. So the numbers are negative 5 and negative 4. One integer and the next one. Right. Okay, then another type of problem you'll see in this section is problems that involve people or machines trying to accomplish a task, and we're given information about them working separately and want to find the information about them working together, or the other way around. What you're going to see is this pattern. The equation you're going to set up is going to be, you'll take the reciprocal of the first individual time plus the reciprocal of the second individual time, and that should equal the reciprocal of the time it takes them working together. And if you think about why this makes some sense, if I take the reciprocal of the amount of time the first one takes to complete a task, suppose the first one takes 5 hours to complete a task. If we do 1 over that time, we get the amount that person can complete in an hour. So and anytime we take the reciprocal of a time, we get the proportion or the part of the task that can be completed in an hour or a minute or whatever time interval we're looking at. So we'll look at this example and I think it'll make a little more sense. So it says an experienced roofer can roof a house in 26 hours. A beginning roofer takes a little longer, takes 39 hours to complete the job. And we want to figure out how long it takes for the two of the people working together to complete the job. And it's tempting right away to think, oh, I'll just add their times. But if you think about it, that doesn't make any sense, because if they each take a certain amount of time working together, they should take less. So we certainly don't want to do 26 plus 39 to get the answer. That doesn't make any sense, right? So just as always, we'll say X represents whatever we're asked to find, the amount of time it takes the two to complete the job together. Right? And what we think about is that the first person, the experienced worker, in 1 hour can complete 1/26th of the project. So we're going to say in 1 hour, that person can complete 1/26th of the project. And the other one, the slower worker, can complete only 1/39th of the project in an hour. And that should represent the total fraction of the job they can complete together in an hour. And the symbol for that would be 1 over x. So this is the amount for worker 1 in an hour. This is the amount for worker 2 in an hour. And this is the amount together in an hour. So we're switching the focus from time to the portion of the task completed. So that's why we're looking at the reciprocals. Then we'll multiply by the LCD. 26 is 2 times 13, and 39 is 3 times 13. So we'll need a 2 and a 3 and a 13. So 3 times 13 is 39. Double that, 78x will do. I'm actually going to write this as 3 times 2 times 13 times x, just so I can see all the factors. So we'll do that on both sides. And I'm going to put that over here. Distribute on the left because there's a sum. The 2 and the 13 drop out, so I've got 3x, and then the 3 and the 13 reduce, so that'll be a 2x. And on the right, just the x drops out, and what did we say, 78, I think, for 6 times 13. So we've got 5x equals 78, or x equals 78 fifths. And if we divide that and get a decimal, 15.6. That makes sense because it should be less than each individual time. It's less than 26, it's less than 39. So we're working together. It takes them 15.6 hours. In the next one, it'll be similar, but instead of being given both individual times, we'll be given one individual time and the time it takes them together. So there is a slight difference here. And this time we're looking for how long it takes Anita's brother working alone to weed the flower bed. And let's keep our time in minutes. So we'll say X is the number of minutes the brother needs to weed the flower bed, working alone. And just like we did in the other one, we're going to switch the focus to the proportion or the amount each individual can complete in a minute. So Anita, for working in 1 minute, can complete a 45th of the task. So that's the amount she can complete working alone. And we should add to that the part that her brother can complete working alone in 1 minute, and that would be 1 over x. And then on the other side, we want the portion they can complete in 1 minute if they work together. So the total time for them working together was 20 minutes. So the portion they can complete would be 1/20th in a minute. So we're just using that pattern. The reciprocal of the first time plus the reciprocal of the second time equals the reciprocal of the together time. And then the LCD, we've got 5 and 9 and x and 4 and 5. So 4, 5, 9, and x would be our LCD. So we don't need to use all of 45 and all of 20. We just need the factors that will eliminate both of those. So on the left, again, we will distribute because there's addition there. On the right, we'll just reduce. So 9x. We'll have 4x from the 1/45th times this group. The 5 and the 9 will reduce. And then we'll have the x's reduce. So 20 times 9 is 180. And then if we subtract 4x, we'll have 180 equals 5x. So x would be 180 over 5, which should come out to 36, right? So 36 minutes. So it seems that Anita's brother is a little faster. She needed 45 minutes, he only needs 36 minutes. So Anita's brother can weed the garden in 36 minutes. I'm just going to double check that 180 over 5 and doing that correctly in my head. Yeah, 36 minutes. Then the last type of problem we'll have are, I call them motion problems. And these motion problems, generally, what you're going to find is in this section, they're going to include, they have a lot of problems where we're moving upstream and downstream or with the wind and against the wind. You always want to keep in mind the general relationship between distance and rate and time. So distance is rate times time, right? If you can think of, this sometimes helps. Miles per hour is a rate, right? That's not every rate is miles per hour, but that's a common rate that we're used to, right? So you can say, okay, rate, miles is a distance, hours is time. So rate should be distance divided by time. And then you can rearrange that as needed to get the others, right? Let's see. So when we're working with upstream and downstream or against the wind and with the wind problems, the actual rate is always a combination of the rate in still water or the rate in still air and the current or the wind speed. If we're going upstream, that's the same as against the current. So the current is slowing us down. So we would take our speed if we were in still water, or just the boat speed, and then we would subtract the current speed because the current is slowing us down. Downstream, that's the same as with the current. So in that case, we would take our boat speed or the boat speed in still water and add the current speed because the current would add to our speed. Right? So the actual rate will be a combination of the rate in still water and the current speed. Similarly, if we're going against the wind, we would take our air speed and subtract the wind speed. Or if we're going with the wind, we'll take our air speed, the plane speed in still air, and add the wind speed to it because the wind would be pushing us along a little faster. So here's how that's going to look in a problem. Example set, we've got a couple examples here. Example 7, we've got the current speed is given as 5 miles per hour. And we're told a boat travels 2 miles downstream in the same time it takes to travel 10 miles upstream. And we're asked to find the speed of the boat in still water. So that's what our variable should be. That's what we're asked to find. Speed of the boat in still water. So again, be very descriptive about that. Don't just say speed. Speed of what? Speed of the boat in still water. Right. And we're given descriptions about how times are related to each other. So we're going to use this formulation. The time is the distance divided by the rate. So we've got basically one situation described in the downstream. It takes 2 miles. So let's make a table. We've got upstream and downstream. And we could have a column for distance and rate and time. So upstream, downstream was first. They gave us a distance of 2 miles. The rate downstream is, if we go back to that chart, x plus the speed of the current, so x plus 5 in this case. And down, upstream, going against the current, we were going 10 miles. And we're supposed to slow down upstream, so we want x minus 5. Let's think about this. This doesn't make any sense. So downstream should be the faster. So let's change this to the 10 here and the 2 there. So that was a bad problem the way it was. We'll put the 10 upstream. Oh, there. 10 downstream and the 2 upstream. Right? We should be able to go farther downstream than we are upstream, right? In the same amount of time. And then the time column, we're going to do distance divided by rate. So the last column will be a combination of the other two. So we'll do 2 divided by x minus 5. And we'll do 10 divided by x plus 5. And then in the description it was given that the times were the same. So that's where our equation is going to come from. So in the same time, that means that the time from the upstream should be the same as the time for the downstream. Then we've basically just got a proportion here. So officially we're multiplying by x minus 5 and x plus 5 on both sides, the LCD. But it's going to look like we're just cross multiplying. So 2x plus 10 is the same as 10x minus 50. And if we add 50 to both sides and subtract 2x, we'll have 60 equals 8x. So x is 60 over 8, which is the same as, what, 15 over 2, or 7.5? And we were talking about speed, and the other speed was in miles per hour, so 7.5 miles per hour. So what do we have? The speed of the boat would be 7.5 miles per hour in still water. All right, then again, if you wanted to check, you could go and put that x back into the other pieces that you had for time. So if you did like 2 over 2.5, let's do that. Two over 2.5. Sorry. There we go. From the 2 over x minus 5, that should be the same as 10 over, looks like 12.5. We get 0.8 for both, so it looks okay. Last example with a plane flying. So it says a plane flies 460 miles with the wind and 345 miles against the wind in the same length of time. This one looks like it's correct, right? With the wind, we should be able to go farther. If the speed of the wind is 20 miles per hour, find the speed of the plane in still air. So again, this is what we're trying to find. So that's what our variable will represent. Or we could just call it the plane speed. It has nothing to do with the air speed or the wind speed. And we can do our chart again with the wind and against the wind. Oops, not wing. And a distance, rate, and time for each one. This time, let's fill in the rate column first. With the wind, we're going to be going faster. So we'll add the wind speed to the speed plane of the plane in still air. So x plus 20. Against the wind is going to slow us down. So we'll take our air speed and then subtract the wind speed. The distances were given 465 for that one, 345 here. And for the time, we're just going to do the distance divided by the rate. So 465 over x plus 20 for the first one, and 345 over x minus 20 for the other one. And again, we've got something about, they told us that it was the same length of time, so that's going to generate our equation. Set the times equal to each other. So 465 over x plus 20 is 345 over x minus 20. Multiply both sides by the LCD, which would be x plus 20, x minus 20. Kind of ran out of space there. Sorry, those should all be in line. X plus 20s cancel on the left, and we've got 465 times x minus 20. And on the right, the x minus 20s cancel, so 345 times x plus 20. And I'll need a calculator here. 20 times 465. 9,300 equals 345x, and then 20 times 345, that should be 6,900. I'm going to double check that. I'm not trusting my math in my head today. Yep, that looks good. Okay, and then we want to subtract 345x from both sides. 465 minus 345, 120x, and add 9,300 to both sides. I'm getting 16,200. I'm going to double check that too. Maybe. Yep, looks okay. And then we would divide both sides by 120. So 135. So the speed of the plane in still air is 135 miles per hour. There. So hopefully that gives you an idea of the different types of problems you'll run into in this section 7.6.